Good morning, everyone. Welcome to EOCP 2023, day 2 of the conference in the water room. So I hope everybody had a great time last night at the dinner and enjoyed the band. And I'm glad you're all here because there was a lot of fun that was had last night. So today we're very lucky to have two gentlemen here from ACC Solutions. We've got Menard and Dhaval Vaghasiya here to talk to us, and they're going to give us a chat about the management techniques for raw water and storm sewer. Just to give you a little bit background on Ray became involved with the water industry when he joined his family's business, Smoky Trout Farm, a recirculatory aquaculture facility in Red Deer, Alberta. They've been helping their customers build healthy fisheries for 25 years. Using knowledge gained, Ray founded ACC Water Solutions with his brother Max in 2017 to bring solutions to municipal, industrial, and agricultural clients across Canada. Ray is currently completing a Master of Science degree at Royal Roads University. Dhaval, who also works at AACC, he has completed his master's in engineering at the University of Calgary and joined their team in 2021. He is an expert on aeration and oxygenation techniques and system design. So with that, I will pass it over to you two gentlemen.
So, are we up? We are up. So good morning, everyone. I'm Ray. My partner here is Dhaval. We're going to give you guys a bit of a deep dive into surface water management techniques. So in municipal cases, that's mostly applicable to stormwater and raw water, but we've done all sorts of other things. Like some towns have community ponds that they need help with. These techniques kind of apply across the board. The biggest area we're going to go into is oxygen, the role of oxygen in water, and how important it is as almost always the first step when we're dealing with surface water that's impaired. After that, we're going to very quickly at a very high level go over some treatment options that may need to be done in addition to oxygenation. So we'll just get going on this. I'll let Dhaval take over.
Hello, everyone. So the part 1 is like issues in raw water and stormwater. Like we'll cover. Okay, sorry about that. First, biological issues. Like whenever we are talking about biological issue, the first thing everybody's mind in comes is algae. That's always issue in stormwater and raw water reservoir. Second, fecal coliform and zooplankton. Like zooplankton is in over here because it's an essential part of the food chain in the water body. If it's not there, they are the transition in between the planktonic algae and the fish. Like it's a medium that fish needs to grow, like it's the primary food. Algae, obviously issue because of the phosphorus or the nutrition that is present at the bottom of the pond. We'll cover it later in detail in this presentation. Physical issues, water clarity, turbidity, mainly because of the algae cells that is contributing to the TSS of in the water body. Like when water is coming into your treatment plant, the main thing is like everybody's worried about TSS. Stratification, that is like the temperature difference between if we look at over here, the last image on the corner, the difference between there is a thermocline, hypolimnon, and epilimnon. Ray will cover it in detail in next slides. Taste and odor, like H2S, nobody likes earthy odor, like when it's coming from the water body, water that you are drinking. So, and the water depth, muck accumulation due to the problems in the like low DO, higher organic content in your water body. So those are the physical issues. Chemical issues, dissolved oxygen, manganese, nitrogen, phosphorus, iron, and pH. So if talk about, dissolved oxygen. Why DO is important in a water body? Why do we need to add more DO into the water body to maintain the water quality grade? The issue, if low DO can create a test, test and odor, release of nutrition from the sediments that is like directly related to the algae growth, harm from algae bloom, HABs, higher accumulation of mucks, and respiratory distress in fish and plants. Yeah.
On this one. So I'm going to spend a bit of time and kind of hammer home the importance of this image. As Dhaval briefly touched on before, stratification happens when we get a temperature differential between the different parts of a water body. So in the summertime, the warmer air at the surface, the sun warms up the surface waters. And as soon as we get a temperature differential of about 0.5 degree Celsius, or a density differential of about 0.5 degree Celsius in a water column, oxygen will not move through it. It doesn't matter how much oxygen you have in your surface waters. If you have 0.5 degree warmer surface waters than your bottom waters, or in the wintertime, vice versa, in the part of the world I'm from where we get ice and stuff. But as soon as that happens, you end up with a stratification where oxygen won't move through. In the summertime, as temperatures warm up in a water body, you get an increased microbial activity in your sediments. So it uses up oxygen. Those primarily heterotrophic bacteria use up a lot of oxygen out of the water column. And they can do it very, very quickly if there's a lot of organics in the water body and the temperatures are warm enough. So all of a sudden you have a situation where no oxygen can get to your sediments, and a whole bunch of chemical and biological processes start to happen at that point in time. As soon as you drop to about 4 milligrams per liter, and this is a generalization, it varies depending on pH and temperature, but as soon as you hit about 4 milligrams per liter of oxygen at the sediment water interface, we start to see a redox of chemicals. The first one that you have happen is manganese. So manganese is the one that starts to dump out of your sediments at 4 milligrams. Some phosphorus will come out at that point as well too, because manganese is often bound to phosphorus in the presence of oxygen. You take away that oxygen, that bond starts to break. When you hit 2 milligrams per liter at the sediment water interface, then we start to see phosphorus and iron come out, because there's another bond there that is oxygen dependent, and they come out in large quantities. Then those little creative, very adaptable bugs on the bottom, your heterotrophic bacteria, they can switch. They prefer aerobic conditions. They like to respirate like we do. But as soon as we get no oxygen at the bottom, they switch over and become anaerobic. And anaerobic bacteria produce different gases. So aerobic bacteria, they breathe like us, they breathe out carbon dioxide. When they switch to getting their electrons from other sources, the byproducts they produce are different. And we get methane, and we get H2S produced, and we also get a higher level of ammonification. So when proteins break down, they turn into amino acids. We end up with a higher rate of that happening under anaerobic conditions than we do in aerobic. So now we've got more nutrients coming out into the water column. So we've got phosphorus, which is a direct algal driver. We have reduced nitrogen species, starting with nitrogen, or starting with ammonia, which turns into nitrite and eventually nitrate. All of those things are lead to productivity in ponds. And we end up with a cycle happening where you start off with a new pond and you get almost no algal growth. It's pretty clean. You get nutrients coming in from your watershed source or whatever your source is, and they drive some productivity. You start getting some algae, some weeds growing. And then those algae and weeds die and they settle to the bottom and they increase the oxygen demand. And that causes the next year even more productivity in your pond, because now we've got that redox starting to happen, and it builds up over time. So you end up with there's a case study. I'll go into more detail on this where we've actually can show how it happened. But it's why when we're talking about managing surface water, why oxygen is so important, why figuring out how to do that. And the science is way more in depth now than it used to be. So it used to be once a month, you go out with a DO and temperature probe, you do a profile and go, oh, it's a shallow water body. Look, it's fully mixed by the wind. We don't have to worry about anything. What we've discovered now that we have 24/7 real-time monitoring available to us and it's affordable, we can put in DO and temperature chains, and we are seeing for brief periods of time, even a few hours every night, where we're seeing a tiny amount of stratification taking place. It might only be 2 inches of water on the bottom of a pond that don't have oxygen in them. And that's enough to have that redox happen. And it's enough to have an increased rate of ammonification and build on that cycle. And as time goes along and your oxygen demand goes higher and higher and higher, it gets harder and harder to overcome that sediment oxygen demand. So I think I'll leave it there and let Dhaval continue on. I just really wanted that in you guys' brains, because we're going to touch on this a lot later on.
Second is nitrogen. like there is a myth that algae is only because of the phosphorus, like nitrogen also a limiting nutrient and behind the algae growth, and especially in some kind of cyanobacteria are there who is just focus on aeration, nitrogen as their source to and grow and just multiply it. So it's very highly toxic to the fish. It's a high oxygen demand. It takes 4, like last bullet points. It takes 4 mg per liter DO2 to produce 1 mg per liter nitrate. So when the nitrogen cycle is happening, like from ammonium to ammonia, then the nitrite, nitrate, and denitrification in anaerobic case, so that just multiplies your oxygen demands multiple times. Like second is phosphorus. It's readily available into the natural, like a natural climate, like in mineralized in rock format. And like erosion happens, it converted into the dissolve, it gets dissolved into the water body. And then there is a water food chain that is over here, like bacterial decay and phosphorus dissolved in water. Everything happens, it goes back to the sediments. Now phosphorus that is in 3 states, orthophosphate, metaphosphate, and organically bound phosphate. So if there are multiple, if we are providing enough oxygen to the bottom of the sediment, and and then it will just decay all the organic phosphorus, and it would convert from sediments to the water body. And if not enough iron is present to bound that and oxygen, then it will just releasing more phosphorus into water body instead of just keeping into the sediment. Major influence sources are like partially treated and untreated sewage, runoff from agriculture sites, and application of some lawn fertilizer. Iron, 4th most abundant element in the Earth's crust. Major source in raw water, groundwater, and sediment. Same thing. Fe plus 3, it's in dissolved state. Fe plus 2 is in a solid state. So if anoxia happening, and then the just chemistry happens in the sediment that converts Fe plus 2 to the Fe plus 3, and which it will just dissolve more ions into. And all these nutrients, phosphorus, iron, low DO, that is the reason behind the like a degradation of water quality in your water body. Either it's a raw water or stormwater pond. Manganese. It occurs naturally in the environment. Again, 0.1% of Earth crust. There are different oxidation state like +2, 3, 4, 5, 6, 7. Only these 3 states are more unstable. Like it's very common that you can find it in water. This +3, 5, and 7 is not really stable. So the thing with manganese is now everybody's paying attention on the concentration. If the maximum acceptable concentration for manganese is, according to the government, is 0.1 mg per liter, but that's not enough on aesthetically side, because even if you have manganese in your drinking water 0.1, as soon as it leaves the water treatment plant and getting to your tap at home, if there is not enough DO present, it will just oxidize in the like a brown, and you probably have seen it on the basin or somewhere that there is a brown color happening like over time. That is because of the manganese. So you can drink manganese at 0.1 mg per liter. It's safe for your body, but aesthetically you need less than 0.02 mg per liter. And if you are taking water directly from the groundwater, you have like a well source as a groundwater, and then it directly goes into a plant. But if like in northern BC and other part of the Canada, they have most of the time raw water reservoir that they will store their water for 1 year, and they will use it treat it and just supply it. If you are not managing the raw water reservoir, then eventually you are increasing the manganese concentration in that sediments. And if anoxia happens at the bottom, you are just releasing back to the water body. So you need now more polymers. Your filter will get clogged while you are treating it. So that's why it's important to manage manganese in the water body.
I'm just going to jump in.
Yeah.
Briefly, I think you have more manganese slides. I'm not sure.
One
more.
Yeah.
Okay. I'm going to oversimplify it and then let him get into the deep science on it. The big thing with manganese, our goal is always to anything that we can do in reservoir before it gets to your water treatment plant tends to save you treatment costs and treatment hassles in the plant itself. It tends to be cheaper to do it in the reservoir than it does in the plant. It's not always the case. You got to look at it on a case-by-case basis. There are a whole bunch of aeration salespeople out there, a whole bunch of companies out there that say aeration will fix manganese. Maybe. Because manganese is really, really easy to prevent the redox of. If you can maintain that 4 milligrams per liter of oxygen at the sediment water interface, you can prevent redox. It's really hard to put back. It does not precipitate easily. You need incredibly high DO levels. You need a relatively high pH and a very, very long retention time. So when you're looking at, if someone's coming along and you go, hey, I've got high manganese levels in my raw water reservoir, we want to invest the money in an aeration system to deal with our manganese. Number one, it's not going to deal with all of it. It never will. Number two, it might not deal with any of it. You might not actually get there. So it's really, really important to have good data on your water body and understand what you're trying to accomplish and if it's possible before you actually invest the money in doing it. So data is really, really important. I'll let Dhaval continue with the hard science.
Sorry, we forgot to mention earlier, if guys have any question, just please stop us and we'll take question as we move forward. So we can solve it like at the time. So this is one of the really good manganese cycle that I got. I think it's probably one that somebody made it and they included all the parameters that affect the manganese concentration into the water. So first, like the light part is like a epilimnion, the bottom part is a hypolimnion, and the green, whatever the green box is, it's like they are just its concentration increases. Like green temperature, like there is a warm water on top, then the bottom part of the water body, DO, pH, bacteria, and manganese insoluble concentration. So now what happened if you have stratification happening in your water body? So I forgot to mention one point that 30 minutes of anoxia can release, let's say, take an example, 10 mg manganese concentration back into your water body from solid to the soluble state. You need 6 days to put that manganese back into the sediment. So even for a few minutes of anoxia in your water body can really increase your manganese concentration. So now your bottom part of the water body, you have low temperature, low LJ growth, low DO. So basically in anoxia, dissolved insoluble manganese that is into the sediments, bottom side, like inflow and outflow, it's just converting into the soluble. Now, when the lake or water body mixes, or if you have aeration that you are mixing your water body, then you are just, so on the top part, you have high temperature, low DO. So that's not a perfect condition for soluble manganese. So basically from soluble, they are converting insoluble, they are converting into the soluble. Now, when they convert to the soluble, this is the first when turnover happens, it goes, sorry, I missed that. High DO, high temperature and high pH is not in favor of manganese, soluble manganese. So we are converting back into insoluble manganese. But if you are not maintaining that concentration, basically over the time, your sediment increase because you are taking more and more water from river, creek, or whatever the water source is. And eventually, at one point, you just have to dredge it. You cannot solve this manganese issue. That's why Ray mentioned earlier that we have to see what kind of manganese are present in there. Again, there are 4 types of manganese: particulate, colloidal, organic, and dissolved. So based on that, we have to provide a solution. There is no one solution that fits for all water body. pH, one of the major parameter that affect all the metals released from sediments to the water column. High pH means low reduction happening. Higher pH, higher ammonia. Like ammonia is like ammonium and ammonia. Unionized ammonia is a toxic, not ionized ammonia. So NH4 plus is not a toxic form. Unionized ammonia is a toxic, NH3. If you have a high pH, then all NH4 is converting into the unionized ammonia. If you have low pH, then your ammonia is in NH4 plus form. So concentration of ammonia in your water body is directly related to the pH. And pH, it changes over the day. Like during nighttime, due to the no sun, no photosynthesis activity, there is a low pH. As soon as they start, it just goes up. And so the pH is directly affecting, like the pH is directly related to the LJ, temperature, and the time of the day.
I'm going to jump in here a little bit. So We see this a lot more when we're dealing with wastewater, where it's more amplified. And it's a bigger concerns because the wastewater operators are trying to keep their unionized ammonia low. LJ, as Dhaval mentioned, is the primary driver of pH changes in water bodies, or it can be macrophytes as well. Plant growth can cause it as well. Respiration reduces pH, so microbial activity, aerobic microbial activity will reduce pH. High photosynthesis levels will increase your pH. So we see, as he's mentioning here, a crossover in the more active photosynthesis that's taking place pushes your pH level up. That high pH causes ammonia to become unionized ammonia, which is toxic. A lot of the fish kills we see in lakes in Canada, they go, oh, we're having fish kills because we had a DO crash in our water body. Fish are really, really adaptive. They can find where the oxygen is in most water bodies. A lot of our fish kills in water bodies actually come because we spike the unionized ammonia levels because we get high algae blooms. So your pH goes up, your ammonia converts over, and that leads directly to a lot of the fish kills that we have. Yeah, I think I'll leave it at that and let Dhaval jump into the next.
So part 2 of the presentation is like potential solution. How do we add oxygen? There are thousands techniques that is available. It's mainly divided into 2 parts, but like different supplier, different manufacturer have different type of design, and they all do the different type of different type of approach to solve it. So I will cover on that, like type of techniques. How do we see that which is good for your water body? There is no one solution for all the water body, like stormwater as well, and depending on your goal. So the role of oxygen in water, like oxygen related impacts, like these are the things that oxygen can affect, like phosphorus, nitrogen, HABs, aesthetic of water, fecal coliform in your water body. Fecal coliform and DO is directly directly related. If you're low DO, then your fecal coliform concentration will go up. And if you have a really high DO, like more than 8 mg per liter, then you don't even have to worry about that bacteria. So what is oxygenation and circulation? So first photo, like the top one, oxygenation, any process that add oxygen to the target part of the water body. Over here, we are not trying to not providing oxygen to the entire water body. We are focusing on it. Like, do we want to add in your hypolimnion? Do we want to add it on epilimnion layer? So there are basically main 4 types in oxygenation: diffuse oxygenation, hypolimnetic aeration chambers, downward bubble contact chamber, and side stream supersaturation, and I will cover that detail in next slide. Circulation, any process that blends water with air or oxygen gas, can be a mechanical or air driven. Basically, surface aerator, updraft pumps, you are trying to add oxygen into your stormwater or raw water pond or any kind of water body by just using the regular like atmosphere air, like updraft pump, downdraft pump, and diffuse air circulation. Reasons for circulation, oxygenation and circulation. This just divides like main difference. They are almost same, but like I'll cover it in a few seconds. Like more oxygenation, you can add more oxygen because you are using almost 90% concentrated O2 into it. Like we can use pressure swing extrovert to like manufacture oxygen directly on site, like more concentrated oxygen, or we can even use we can get 100% pure oxygen from the supplier, but you have to build a tanker near to your water body and it might be expensive. It reduces release of iron, manganese from sediments, like as we talked about it earlier. Reduce accumulation of sulfide and ammonium. It reduces release of phosphorus from bottom sediment. So it basically limits the algae growth, but it's not direct. It's not like you are adding oxygenation system today and suddenly after 1 week your algae will go. No, it takes some time. You want to put all of your like metals, ions, that is a driving factor for algae, you want to put back into a sediment. It reduces sediment oxygen demand. We'll cover this word in detail in next. Like this is really important to understand the sediment oxygen demand of your water body. Circulation, it adds more oxygen, definitely less than the oxygenation system. It it basically homogenizes the entire water quality of your water body because you are mixing it. So more acceleration of pH equilibrium throughout the water body. It decreases LJ through the buoyancy, like BR, and increasing exposure of fecal coliform to the UV lights and reduce concentration of metals like Fe and manganese. First one, diffuse oxygenation system. It's really great system. The only problem is you need more than 15-meter depth to use it. Because if we are putting this system less than 15-meter depth, we are just wasting oxygen because it will release back to the atmosphere. Ray will cover on this one more.
Yeah. So this is a strategy. It's not new. It's probably been used for about 15 years in the United States. I think there's one project in Europe. And as of about a month ago, there's one project in Canada. So these photos here are from Elk Lake on Vancouver Island. It was a lake where scientists by the name of Dr. Paul Ganser designed this system and then also came up and installed it for them. And he's a good friend of mine, so he asked me to come out and help, which was pretty lucky. The concept behind it is when you have enough depth, you can actually diffuse oxygen bubbles into the hypolimnion, and they will fully dissolve before they reach the thermocline, or if any make it through the thermocline, there's not enough power there to actually cause any kind of mixing. So we're trying to maintain stratification in the water body. The model for it is basically you have a pressure swing oxygen generator. You can get 90 to 92% concentrated oxygen in that. It is fed through that very big long pipe all the way out to where you get to the bottom, and then it is fed through the diffusers. You can see attached to the pink hose there. That's literally just like soaker hose. It's very similar to the stuff you'd use for watering your garden. It's just a lot higher quality. It's going to stand up for a long time. And every single one of these orifices there, they have different sizes. They're different sizes depending on your depth, because you have to equalize your system. So when you design the system, you pick your area of the water body that's 15 meters or more depth. Some might be 20, some might be 17. If you try to just flow the same flow to all of them, the pressure of the water will keep it from flowing evenly. So there's a lot of engineering that goes into this. It's quite a complicated process, but it's highly effective. Challenge: we actually don't have a lot of lakes that are, especially in the prairies where I'm from, we don't have enough depth in a lot of our lakes to actually use this as a potential solution. And it is a lot. Like if you look at the length of that, Elk Lake's not a very big lake. You think about a truly large water body. It might not be cost effective to do it. You have to have a secure place on shore to put your oxygen generators. So there's pros and cons to it. It's highly effective. It works well. Probably has one of the highest success rates in terms of different forms of oxygenation and aeration, but not the right fit for everything. Oh, next one. So hypolimnetic aeration. The idea behind hypolimnetic aeration is it's kind of a cross. It's a little bit of oxygenation and aeration. So there's different models out there, but basically what the system is designed to do is to suck water from the bottom of a water body, bring it up to the surface where it either interacts with atmospheric air or you expose it to pure oxygen, and then you bring it back down to the bottom without disturbing the sediments. The problem is it's insanely expensive. It's hard to put in. Like if you look at the size of these things, it involves giant cranes. You will always have a big thing on the surface of your water body. So if you're talking recreational water bodies, that type of thing, it's just not always very, very practical. There was a big fad here in, I want to say they were used a lot in the 80s and 90s, and then they kind of disappeared because people didn't realize they were that effective. And then here about 10 years ago, there was this new resurgence of do this again. And it lasted about 3 years and disappeared because they just really were too expensive and too awkward to deal with, too clunky of a system to actually deliver the results that we wanted to see. This is one of the more common oxygenation techniques out there. It is a species cone. So a species cone is where we draw the water from the bottom of the water body. We flow the water down through the system. We bubble oxygen up at the same time. And if you match the flow rates right, those bubbles will never go all the way up. They will fully dissolve before they go out. And then the fully saturated oxygen flows out the bottom, and you can put it wherever you want in the water body. And there's a bunch of different models in these. Some are shore mounted, so they become part of a side stream system. Some of them are mounted on the bottom of a water body. It's really, really effective. It's relatively inexpensive. There's some systems that have been in place since the 70s in large lakes in California. The big problem so far has been, up until very, very recently, they were incredibly cumbersome. They required big oxygen tanks on shore. They were giant stainless steel units that you had to figure out how to move into place in the bottom of a water body. They were hard to do maintenance on. So there has been some updates on this over the last few years. It is still a very, very effective way of doing oxygenation, and probably has one of the higher success rates in terms of actually delivering results. Side stream aeration is basically that same concept as a species cone model, except for we're actually drawing the water off the bottom, fully oxygenating it on shore, and then injecting it back into the bottom of a water body. The pictures that you see there, that was a pilot project I worked on with Dr. Ganser in Florida a few years ago. We really thought it was going to be the end all and be all. We were like, this is such a great thing because we're going to draw the water out. We're going to keep it the same temperature. We're going to put it back in. It's not going to cause any mixing. This stuff here, the big key with this system is you want to, because you're dealing with smaller water bodies where it's really, really easy to cause mixing. We want to avoid mixing at all costs. So this system is designed so that as it sucks the water in, it creates no turbulence in the water. These tubes have thousands and thousands of little slits. So you might be doing, say, 10 gallons per minute that you're sucking into the system, but it's so spread out that it doesn't actually create any turbulence in the water. And then when we put it back in, it does the same thing. But we had a problem. There was no way to actually keep the water from changing temperature by more than half a degree. So there was always going to be some exposure to warmer temperatures as you pumped it up through the water. The pump created heat. Exposure to sunlight created heat. And as soon as you created more than a half a degree difference in water temperature, there was enough of a density change that even though our goal was to not mix, we mixed it. And that led to the development of the OST, or the oxygen saturation technology, which is the same idea, except for everything sits at the bottom. And where it has an advantage, so it's got a species cone-like device in there. The advantage of this over top of the big old traditional species cones is you can float that right into the middle of the water. It's got that collar on it. That collar, we fill it with air. We float it, both of the intake and the outtake canisters, which are the same ones I showed you the picture of before. They have flotation devices on them as well. You float it to exactly where you want it in the water body. Kick on your trash pump, fill those with water, and it sinks to the bottom exactly where you want to have it. You need to do maintenance on it. You plug in a compressor, you float it up to the top. All of the maintenance can be done from the surface of the thing. So it's changed things. It's side stream aeration, but it's not side stream aeration. It allows us to maintain the temperatures because we're not pumping the water for long distances. We see no temperature change. The water itself keeps the system cool. It is probably the biggest jump we've had in oxygenation technology. Nothing new in it. Just the way that it was applied, it allows us to use it in small water bodies, minimum, as long as you got about 8 to 12 feet of depth, you can usually find a way to make this work. And downside, pretty big capital cost. Upside, easy to use, easy to put in, and very, very low operational costs. So there's very, very little maintenance and costs that are associated with it. This is just an example of a job in California that one of my friends put in, owns a water management company there. And you can see there's a dashboard. These have sensors built into them. It's one of the great advances in technology. We put a DO and temperature sensor in, and we can set the band that we want the device to operate in. So at 8 milligrams, if you say, I want to maintain 8 milligrams per liter minimum in my water, which is a pretty good target if you're trying to precipitate metals and stuff. But we don't want to go over 12 because then we're just wasting oxygen and energy because it's not helping us accomplish anything. The system will turn itself on and off and maintain those levels. So your operating and energy costs are very, very low. We're not trying to mix the entire water column. We're moving a very, very small amount of water because as we inject that fully oxygenated water out into the bottom of the water body, that oxygen moves very, very easily. It diffuses through similar densities of water. So within a few days, you can see in this particular little pond, This is the day it was turned on. And I can't quite read the dates here, but it was, I think, about 2 days, Dhaval?
Yeah, 20, yeah.
About 2 days, the oxygen levels, because it was already homogenized. The temperature wise, it was pretty well mixed, but there was so much sediment and oxygen demand that the homogenization, the oxygen movement from the surface couldn't keep the sediments oxygenated. So within 2 days of adding this, we see the oxygen levels are returned to the levels that we want. And then as the system turns itself on and off. So it's a very, very effective, practical way to do things. It's not the right fit for everything, but it's a pretty good solution. Do you want to do this one or you want me? All right. So circulation. So with circulation, we're not adding oxygen directly to the water, or we're doing very, very little of it. Our goal is to take advantage of the surface transfer of oxygen. So, and it's primarily wind driven. So the limitation of all mixing style systems, no matter what they are, is a huge amount of that transfer rate comes from we're trying to circulate the water body, and depending on wind speed, it's going to be that's going to be the limitation that you have on how much oxygen you have. Surface areas are a little bit different. They do agitate the water. So whether you're talking a fountain or an agitating unit, they will increase the surface transfer rate, but they don't circulate water well. So any type of circulation method that can't actually get the entire water body turning over, you're going to not get enough oxygen down to your sediments, which is the absolute goal, is keeping the oxygen levels high at your sediment level. So they're good, used in combination with other technologies like bottom diffused aeration or other circulation techniques. Surface aerators can definitely help a lot. On their own, the only reason that you would ever put in a fountain in a pond, like a stormwater pond or anything like that on its own, is aesthetic. You might convince yourself, like a lot of, we do a lot of towns where all of the residents are like, we need a fountain, we need a fountain. You come out with the fountain's not going to solve the problem. They put in the fountain, problem's still there. Now they're just spraying green water in the air instead of actually getting rid of the green water. Downdraft pumps, solar bees, updraft pumps, solar bees. These are incredibly energy efficient. They run completely on solar. You don't have to plug them anywhere. The real downside of them is they don't actually work. There was thousands of these things put in all over the world, Europe, Canada, the United States. The problem is they do not create enough water movement to actually deliver oxygen to the sediments or even increase the oxygen in the upland and all that much. The quote that's on there: water circulation generated by solar bee resulted in weak velocity fields to a lateral distance of 5 meters from the device to a depth of 1.5 meters from the surface. So this is a peer-reviewed paper analysis of solar bees and how well they work. So if you've got a large water body and you're saying, oh, I know I need to mix the whole thing, I want to homogenize my water column, do you have any idea how many solar bees you would need if it only has an area around each one of 5 meters that it's having any actual far field oxygenation effect, and only going down 1.5 meters? It's a lot of money to invest for very, very low results. Downdraft. Same idea as a solar bee, but it pumps water down instead of water up. Same kind of limitations as the solar bee in a lot of ways. And the other real downside of them is just how you can see the size of that unit. Like that's a crane. To actually get them in and make them work, you need so many of them because they've got such a small field distance around them. They actually create positive effects. The capital cost of them, and then the headache of keeping them running, and a lot of times the energy, because moving that much water takes a lot of energy. The solar systems generally don't deliver enough to give you the results that you want. So this is probably the most common one. This is where we cut our teeth as a company, doing tons of aeration systems for little fish ponds. The goal of bottom diffused aeration is the bubbles add a little bit of oxygen to the water, but not a lot. And unless you've got really, really deep water, there's just not enough time for much transfer to take place. The goal is to mix the water body. The goal is to circulate the entire water column. In order to be effective, you have to have enough energy to break stratification. So depending on the size of the water body, you have to entrain enough water with that, with your bubble column to fully mix your water body. It's got some of the limitations of updraft and downdraft. There's a certain field, and Dhaval's going to go really deep into this because with us, what happened is we've been installing aeration for a long, long time, and we started going, okay, we've been telling all of our customers that we're going to fix this problem and that problem with aeration, and sometimes it works and sometimes it doesn't work. And about 3 years ago, we recognized that we needed more knowledge and we needed more science, and we needed to understand why what we were doing wasn't always delivering what we did. And that's where Dhaval came in. He was hired specifically for the purpose of making us better at this than anybody else in Canada, where we understand the science. And he's going to do a really deep dig into it as we go further. So I don't want to go too far into this. It can be a highly effective tool. It's cost effective. They're relatively inexpensive compared to other strategies to put in. It requires a fairly low amount of energy to move a lot of water, but design is the key on it. And I think you guys have seen some eyes, some yawns. Time for a coffee break? Yes, no? All right, let's take 10. Well, we're gonna try to push people to ask some questions. I'm gonna remind them again. So I'm gonna handle the question. It's really my virtual. Yeah, she did. Yeah. Yeah. So I'm gonna handle the virtual question and then let you get going. I think it is. For us, yes. Just go slow. Step by step. What's that? Yeah. Okay, we'll get started again here. If apparently we had a question come in from the online audience, so we'll hear that. And also just want to remind you guys, if there's any point in time that you want to throw your hand up and you have a question, please do so. Just wait for somebody with a microphone to get to you, because it's really important. The online people won't be able to hear you if you you don't ask the question without with a mic. So let's get that question.
Yeah, so we do have the online question. The question is from Ryan. Could this oxygen saturation tech help with algae blooms in an open ditch irrigation canal of an average flow of 40 to 90 CFS?
The simple answer is I don't know. I don't have nearly enough information to be able to say this solution works. So it's possible. We would need to see the data. We need to know the size, the depth. We need to see some sampling data. We need to see some DO and temperature data. So it's a possibility, but it really depends on a whole bunch of factors. And I'm pretty hesitant to ever give advice without having enough information to make a definitive answer. So if that person wants to reach out to me afterwards and share some more data, I'm happy to look into it for them. I'm going to let Dhaval dig into the what we've learned over the last 2.5, 3 years about aeration and how to do it wrong and how to do it right.
So the first we clear like type of area oxidation technique and circulation technique and everything. This part I'll cover on what are the factors that affects on designing side. What will decide that your system is going to work or not. So first, keys to successful circulation. Sorry about that. So as Ray mentioned earlier, majority of oxygen from the circulation technique, like any kind of aeration, it's not coming from bubbles, it coming from the wind. So majority oxygen comes from wind, not bubbles. What we are trying to do, we are trying to mix the entire water body. So the always like in first couple of feet, like maybe 3 to 4 feet of the water body is always saturated with the oxygen, like super saturated. And we are just trying to mix it and so dissolve that, homogenize that DO into the entire water body. Now the myth was before that, like if anyone to ask like any company, they're like, we need aeration. They will design a system based on this number. What is your surface area like in acre of your water body? You're saying 10 acre. You will get number, okay, you need 13 cubic feet per minute air. And depending on, they will give you maybe 5 diffuser, 10 diffuser, 15 diffusers to solve your problem. They don't know, we don't know what we are doing based on that because we don't have data. We are just guessing the number. We don't know how your sediment looks like. It's 80% organic, 20% inorganic, 20% inorganic, 80% organic. If that's the case, like, there is no way aeration can solve that problem. So the goal with the circulation technology is to maintain the temperature difference from surface to the bottom less than 0.5 degrees Celsius. If you have aeration, if you are wondering it's working or not successfully, 100%, just go with your temperature sensor, measure the temperature first 1 feet below your surface and measure the temperature 1 feet above your sediment. If the temperature difference is more than 0.5 degrees Celsius, basically it's undersized aeration system. Anybody, like if you are not maintaining the temperature homogenized, then it's not working. And the biggest challenge on the aeration, we are trying to overcome the thermal gradient. That is all, like we are trying to overcome the thermal gradient of the water body, the temperature difference. It's very hard. Like it's not that if you are putting some diffuser and bubbles into it, it will mix it. Thermal gradient, like the temperature difference, density difference is huge. If you are putting one diffuser over here, it might will affect only this area, but the remaining part is just like that. So basically it's undersized. And what happened when it's undersized, you are moving all the nutrition rich water from the bottom to the top part of your water body. And basically algae has more nutrients to grow. They have photosynthesis activity going on. So even after putting aeration in, you are not seeing any improvement for a couple of years. And we have the case, like I'll discuss in detail, that one area, okay, we'll do it in detail. Sorry, I don't want to go it in detail right now. So another thing, like the depth matters. If you have the same size of your lake or water body, whatever, and let's say the depth is only 3 meters, it's very shallow, and the one is like 10 meters, surface area is same. To get the same result with the circulation, you might need in shallow lake, or you might need 4 diffuser, but the same result you can get in the deeper lake with just 2. So in circulation, depth matters. If it's very shallow, you need more diffuser to mix it. If it's very deep, you might put 2 or 3 and it will work. This is just turnover, and the successful, how do we measure, like based on the turnover, like how many times you are turning, like mixing your entire water body. So if you look at the graph, this is just a depth, like let's say you have 3 meter depth in your water body and the volume. So if you're putting just 0.5 CFM per acre airflow, you're just mixing maybe 1% with but same airflow. If you have 15 meter depth, you're mixing 25%. So depth matters in circulation. And the area, mixing depth, like the area of turbulent flow near to your diffusers, is mostly 2 to 3 times the depth of your water body. So if let's say we are trying to get rid of LJ in your water and we need turbulence. So the more turbulence you will get is just, let's say it's 5 meter in depth, you get turbulence just up to maybe 10 or 15 meters. After that,
I'm just going to jump in here and we didn't touch on this before. We should have. There's 2 types of algae that or broad classifications of algae that we're looking at. We're looking at cyanobacteria, which is basically a photosynthesizing bacteria. Cyanobacteria have vesicles in them. They can fill these up with air, they can deflate them, and they can control their buoyancy in the water column. So when we're talking about near field mixing and turbulent mixing, what we need is enough energy in the water to overcome the positive buoyancy of the algae. Because if we take them out of where they want to be in the water column, they don't do well and they eventually will die. And just to give you an example, I did some sediment coring in Moose Lake in near Bonnyville in Alberta. We were coring in 60 feet of water. I found blue-green algae sitting on the surface of the sediments in 60 feet of water. That is how versatile they are. They will go all the way down to the bottom, collect nutrients, float themselves all the way back up to the surface to get sunlight to photosynthesize. If we want to deal with blue-green algae, mixing them is an effective strategy, and a lot of people sell aeration systems as being that strategy. If you don't keep into mind 2.5 to 3 times the depth is the only area you're going to get turbulent mixing in, you will not overcome that positive buoyancy and your system will not deliver the results that you wanted. Now you can talk.
So how do we select? Oh. No, it's jump.
So there's 2 things we're looking for in an aeration system. If we're dealing with near field mixing, we're talking about the area that we can create turbulent mixing that overcomes the positive buoyancy of cyanobacteria. Far field mixing is the amount of full circulation we get. So it's not going to be turbulent enough to overcome the positive buoyancy of algae, but it's still going to be enough water movement to break the thermocline and provide top to bottom homogenization in a water column. There's a whole bunch of discrepancy on this out there in terms of all of the different suppliers. Like I've seen people make claims of, oh, our magic aerator will mix 10 times its depth or 15 times its depth or 20 times its depth. It really, really depends. Well, to be honest, it doesn't depend on anything. It doesn't matter what size of diffuser you have. There's limitations to how far around a diffuser you'll get effective far field mixing and oxygen delivery to the sediments. In our experience, and this is just us practically out in the field doing it, at best you were looking at 7 times depth of the diffuser in terms of area around it. In most cases, closer to 7 than 10 times. Even the turnovers today, that there's not a lot of solid science out there when it comes to making these calculations. So when we say the word assumption, in a lot of cases, when we're talking about the fluid dynamics of aeration in water, it's a best guess. Like it's not bang on exact science. So it's really easy to undersize the system. If you use that initial calculation that Dhaval showed you, it was a calculation that was developed by two scientists, Lorenzo and Fast, in 1977. Almost everybody who is designing aeration systems out there right now is using that calculation, and it undersizes the systems in almost all of the cases because they don't end up with enough diffusers because they can't get that near and far field mixing that they want. Anyway, go ahead, Dhaval.
So how do you decide which system is best for your water body? Like proper selection. This is a graph that I took it from Dr. Wagner's oxygenation and circulation study. It's a really good study, 250 page, but goes into a detail and 12 countries, like different system. So first, it depends on the depth, sediment features, and water quality issue and goal. So first we need to decide, like, what's your goal? Like, do we need to just handle manganese? Do we need to just improve the overall water quality? Or you are focusing on manganese? Depending on your goal, there are different variables that comes into play, and based on that, we'll design a system. Hypolimnetic volume of the water body is greater than 50% of epilimnetic volume. Yes, oxygenation is preferred. No, go to the circulation. If now oxygenation or circulation, both option is available. Now, maximum depth is greater than 50 feet. Yes, again, oxygenation. No, go to the circulation. So based on all this step, it will help to the end client, like towns or municipalities or private who wants to put aeration, like what is the best criteria? Like it's not like sometimes even surface aerator is the answer for your case. Like you don't have to spend $100,000 to put a bottom diffuse aeration. Surface aerator will work. Sometimes it will not. So this is just one of the chart that I just wanted to show you that how it works, and like cost benefit analysis assessment is necessary. We'll talk about this in detail. Like if you can solve 80% of your problem by spending maybe like $50,000 system, great. If you want to solve 100%, then you have to spend $200,000. So is it valid to, like, you are spending $150,000 more on a system that can only give you 20% more result? So that is also an important factor. This is another graph that I made from that study that I mentioned. It was done in 2015, was funded by UK Water Industry Research and Water Research Foundation. It includes 73 oxygenation and circulation systems from more than a dozen countries: US, Canada, India, China, Australia, New Zealand, all around the world. And they are most installed in drinking water reservoir, but also from some recreational lakes. So if we look at the system, do you want to do it? Yeah, okay.
Really what this was is unfortunately, there's a lot more aeration systems than this installed in the world, but there's not enough data on them to do a full analysis. Most people, you say, hey, is your aeration system working? And they look out and, yeah, I see bubbles, so it must be. If you don't have proper parameters to judge whether a system's effective or not, in other words, if your goal is this, and this, is it meeting it, or how much of those goals are it's meeting? So Dr. Wagner was limited in having only so many things to look at that had enough data, but it still was very, very telling. It was a high enough number that we got a pretty good idea of what works and what doesn't work. The one on the far left, this is your solar bee. Solar bees are expensive. They work 14% of the time. Probably not the best solution to choose. On the far other end, we're looking at a hybrid system where you're combining oxygenation and circulation together. Unfortunately, there's not a big enough pool to say, yes, for sure, this is something that'll work every single time, but it did. It's the only thing that showed up with an absolute 100% success rate of addressing all of the problems that it set out to do. The one that we talk about the most is our bottom diffused aeration systems. It only met all of their goals in about 55% of the cases. And we'll touch on a little bit later why that is, why so many of them aren't successful. But when it comes to municipalities or anybody dealing with raw water, that cost benefit analysis is incredibly important. How much is it going to cost to put in? How much does it cost to maintain it? What is its energy use? And what are the maintenance costs? What's its life cycle going to be? You've got to do all of those things and then measure how much chance of success you think you're going to have it before you should be making a decision to do it. Like we get so many calls from small municipalities where they pick up the phone and go, yeah, we have a stormwater pond or we have a raw water pond. We have these problems in it. We know we need aeration. Give us a system. And our initial response is always, are you sure you know you need a system? What data do you have? What do you think that you're going to accomplish with it? And the more data we have, the better job we can do designing a system, the more certainty we can give people whether or not it'll work. Go ahead.
So now what are the factors that needs to be affecting on oxygen demand of water body and during the designing of system? I missed to include this one. So when Dr. Wagner did this study, they realized that these are the 5 main reasons behind the failing of the system all around the world. It doesn't matter where you are. Failed to include oxygen demand, installation of fewer units, undersized system, failed to include incoming water oxygen demand, undersized, and failed to include sediment oxygen demand. So when we are putting numbers like, okay, this is your water body, what are the factors that affects? Like the regular one, like just people think about it is surface area of the water body. If you have 10-acre surface area, you need this much CFM, done. Volume of the water body, depth, current DO, and temperature. That's the most thing that is included in any kind of aeration that everybody's installing. And we were even doing that earlier, 3 years ago. Then we change our technique. And this is the thing that comes into play. Elevation of water body. Wind speed. This is the most affecting factor. Like we talked earlier, in circulation, oxygen comes from the wind, not from the bubble. Bubble are there to mix it. Sediment oxygen demand, incoming water oxygen demand, induced oxygen demand factor. Induced oxygen demand factor is like, you have at the sediment, you need maybe 4 mg per liter. But when you are mixing it, you are just multiplying 4 times the oxygen demand. And most of the time that if aeration system is undersized because of this one, nobody includes in their calculation. They think that, okay, this is a number, they need 20 kg O2 per day to solve the problem. But when you are mixing, you are just multiplying 4 times. So now you need 80 kg O2 per day to see the same result. Bathymetric map. This is very important. Like we have installed one system in Langley, BC over here. And when you look at that bathymetric map, it's 53-acre surface area like stormwater pond. But if you look at the bathymetric, oh yeah, go ahead, sorry.
Why elevation speaks to
Pressure, oh, sorry, yeah.
Sorry, why the pressure just because of, or sorry, elevation just because of pressure or something else?
So elevation, pressure, temperature, like oxygen has its limit. But if you go more on elevation, let's say you are at sea level, you get the maximum, you can dissolve 10 or I think 11 O2 in 1 liter of water. If it's 600-meter elevation, the maximum capacity is 8 kg. So there is no point to design a system at 11 because you are just wasting. There is no way you can dissolve all the oxygen. And that is also elevation and I would say location. So we have learned that one company, example, work is established in the Ontario and they are doing project over here in BC and in Alberta, and they forget to consider the temperature change. They realize, okay, if whatever we design a system in Ontario, it work for over here, winter comes and water freezes and the pipe just bursts. And it's a more nightmare. So also depend like elevation and location, like what you're working with, how do they know your geography of the area, like temperature, how it looks and everything. Now that is the factor that affect the O2 demand. Let's say what factors needs to consider during the design of the system. Type of system, surface aeration, bottom diffuse aeration, and oxygenation, as I told you earlier, by looking at the charts that based on this chart, it depends. Like sometimes it's not like bottom diffuse aeration is the answer for everybody. We need to analyze the site water body and based on that, the suggestion. Type of diffuser, there are 100 types of diffuser available. Do you want to pay more upfront and don't want to do maintenance, or you just want to replace your diffuser every 5 years? So that types of diffuser, number of diffuser placement, airflow meter for each diffuser, pressure gauge meter, and type of compressor. So wind, like this is just, I got the data just 2 days ago, like how average wind looks like in Vancouver. So if we look right now in starting of September, if we look at the wind pattern during the year, and this is the average of, I think, around 10 or 15 years. So in winter months, when its wind speed is always high. And when we need actual oxygen during this summer month, like June, July, and August, wind speed is low. So basically we need to work more, like compressor need to put more air in summer month compared to winter month to get the same level of oxygen, because in winter month they have higher wind speed can add more oxygen, like it can help on the aeration side, but in summer month it's not like. So we also need to consider the fact, like what's the worst condition, the design during the designing time, what's the worst condition can happen, and design a system based on that condition. So even if winter month, yeah, it will work great because we are designed for the summer one, right? So now this is another, like I put the number, like let's assume the temperature is 25, surface area is 1 acre, and DO saturation at that location, like maximum you can do is 6.86 mg per liter. Now, and this was the data that we used from Rowe and Hunt from 2007. They just develop an equation, and if you put like elevation numbers and kinetics and everything, then it will give you how much effect it can have. So your current DO is only 2 mg per liter, and your wind speed is just 0.89 meter per second. You can only add 0.9 kg O2 per day. That's if we are not changing anything, instead of wind speed 0.89 meter per second, it's 2.68. We can suddenly add 6 kg O2 per day, just based on wind speed. And so this is just a graph like how wind speed data is important while we're designing a system. This is another study that did Monjur and Takashi in 2000, that how artificial mixing of lake water body, bubble plume, and effect of bubbling operation on algal bloom. So this study is based on this total chlorophyll A data, and they measure it in kilogram and to see like how it affects. This shows why lot of people came to our booth, like we have a question in quiz, like what is most important in aeration system, like a number of diffusers, airflow, or both. Number of diffuser will show like how number of diffuser is more important than the airflow in this one. So this is a graph. They did one aeration. The graph is from April to November, and it's total chlorophyll A in kilograms. So what they did, that effect of number of pots on total, like number of diffusers on the total chlorophyll A concentration. So for each system, the airflow was constant, 25.42 CFM airflow cubic feet per minute. Number of diffuser, they change it, airflow constant, system starts time June. So another effect, that when you install system, like when it started, June, July, or like a September, it also affect your results on the aeration. So on this one, each system started at June. Like when there is zero diffuser, no aeration, this is the graph, solid graph of the chlorophyll A in kilograms. With 5 diffuser, same airflow is 25, and the system started in June. Instead of decreasing the chlorophyll, because aeration should decrease the algal bloom, right? So, but it's not, it's just deteriorating the water quality more. The concentration of total chlorophyll A is increasing, but with the same airflow, if you have 10 diffuser, the blue line, you are getting some result. You're not changing the airflow, you're just changing the number of diffusers. But I don't know what this marker stop working. Yeah, at 20 diffusers, the red line, you are looking at the real change. Like you can see the difference. Like why number of diffuser matters on aeration than the airflow. Another graph. So if you look at the reduction of chlorophyll A in percentage and airflow, like let's take 21 CFM. So that is like 10 liter per second. In this one, the airflow is same, just the number of diffuser is now 10, 15, and 20, not 5, 10, and 20. So if you look at 10 diffuser, the last one, no, sorry. Yeah. So if you look at 10 diffuser and 21 CFM, you get a reduction maybe 5%. But without increasing the airflow with 15 diffuser, you are getting at 38% maybe. And with 20 diffusers, you are getting 45. Now they increase the airflow from 10 liter per second to 15 liter per second. And yeah, they're getting some result, but it's not as good as by just increasing the number of diffusers that work from 10 to 15. Now, when I was saying that we need to do that cost benefit analysis, like what is the maximum? So that comes to in play over here, like 74 CFM. You are putting 74 CFM and 20 diffuser. So the result, the reduction in chlorophyll A you are getting is almost same. Like with 21 CFM, you can get 45, and at 74 CFM, you can get maybe 46. So is it worth to spend more money on how big a size blower or compressor to just increase the airflow? This is another, now they are focusing on the time. 5 diffusers, airflow is constant, but system start time changes. So one thing with aeration is you want to start aerated your water body before the problem starts, like, or before the problem develops. So you want to start as soon as spring hits, like April, May, and so there is no chance that LJ will develop. Once LJ or anything, any problem is there, it's very difficult to get rid of it. So if we talk about it starts time in June or one in July, yeah, June, July, and May. It doesn't matter the doesn't matter the start time because the system was underside. So 5 diffusers, doesn't matter when you start the system, you are not getting any improvement. But with the same thing, with 10 diffusers, if you are starting in May, you are getting good reduction in chlorophyll A concentration compared to if you start system at June or July. So number of diffuser, starting time of the diffuser is matter. Now the keys to successful aeration, like aeration benefit and cost analysis. This is the graph I was talking about. Like if your system or your whatever municipality or town spending money to the getting the system, that falls under on this area, that you are just undersizing, you are risky. It's very risky area. Like you will not see any improvement for a couple of years, definitely. You will eventually, sometimes after 10 years, 15 years. So, but this sweet spot, it's very difficult to find because after that, whatever the money you are investing on your system, you're just wasting it because you are not getting enough return on your investment. Case study, I think they will get that.
Yeah, well, we're just going to go through some examples of sort of when we changed our business model from, oh, look, we're going to blow bubbles in the bottom of your pond, hope it works, to let's truly understand the water body and what's going on in it so that we can give customers really, really good advice. So this is a raw water reservoir in Morris, Manitoba. We were approached by them. They had both manganese concerns and LJ concerns, but the manganese were the bigger concerns. It was causing them more problems in their plant. And given the budget they had available, they decided that, well, let's focus on the manganese first. This had an existing floating lateral arm aeration system in it. So a lateral arm aeration system is sort of bottom diffused aeration, but sort of not. So basically they run big pipes out across. They use them in wastewater, they use them in raw water reservoirs they're all over the place. But the oxygen delivery or the air delivery system floats across the top of the water body, and then it has arms sticking out from each of those columns, and those arms move up and down as the water level goes up and down. And suspended below those arms are diffusers. So there's a couple of big issues that this causes. One of the big problems that these guys had is they were spending tens of thousands of dollars every single season fixing this system because they were in an environment where they got ice every single year. Like you're in Manitoba, it's -40. It doesn't matter how well you mix your water body. It doesn't matter what you do. You are going to get ice forming across the surface of that water body. Ice is pretty interesting stuff. It freezes onto something, you get a little bit of wind, the ice breaks up in the spring, it will tear huge pieces of infrastructure apart. So that was one of the big problems they had. The other problem they had is they were pumping tons of air into this water body. None of it was getting to the sediments, except for a very brief time every year when the water level was low enough in the reservoir that they were actually getting some mixing happening. So they approached us and they said, how do we fix this? And I went, I don't know. What do you have for data? And they had a little bit of dissolved oxygen and temperature profiles, so we knew about the mixing, but it was the manganese we had the real questions about. Where is the manganese primarily coming in from your source water, or is it primarily coming from redox? So the first thing we did, after analyzing their temperature profiles and understanding when the water body stratified, is we looked at their manganese, and we looked at the times a year they saw spikes, and we actually went out and did the sampling and figured out that when they had anoxia happening at the sediment water interface, it was driving the manganese in the entire water column. So this means doing DO and temperature profiles, doing top and bottom water grabs from multiple places in the reservoir, sampling the source water when it's coming into the reservoir. So we came back to them and said, the way that you solve this problem is or manage this problem, because you're never going to solve it all the way. The best way to manage this problem would be upgrading the in-reservoir portion of your aeration system so that we get full mixing, which is what we did. So we kept in their building here, they had their existing compressors, they had infrastructure going through the berm here. In order to keep their costs down, we made the decision that we would reuse as much as we could of the existing infrastructure. And then on the shore, we put in flow meter manifolds and ran new line to 18 diffusers on the bottom. So based on the depth, we knew we could get full far field mixing. We weren't going to get enough turbulent mixing to deal with the LJ, but we knew that we were going to get enough mixing with the airflow that they had in those number of diffusers to fully homogenize the water column most of the time. So these are our, we manufacture these diffusers ourselves. This is the cost benefit analysis part. We offer a 10-year, no questions asked warranty on that diffuser because they're tough as nails. They're made of industrial stainless steel. Our the diffuser discs that we use, we've had some of them in water bodies for over 15 years now. When we're dealing with municipalities, you guys are looking long-term. We want to make sure that we're giving you stuff that isn't causing you headaches, isn't causing you hassles. A lot of diffusers on the market that actually, they're a little bit more efficient on the oxygen that they deliver. We chose not to use them because they have to be either pulled up and cleaned with an acid or fully replaced about every 5 years. So when we do the cost benefit analysis, we're like, oh, well, maybe it's better off that we, slightly lose efficiency during the first year or two of operation compared to the competitive model, and in exchange, not create a whole bunch of operational hassles for the operators. Other thing that we do in all of our systems is we put in flow meter manifolds. The traditional way of doing aeration is you have this big long line of ball valve manifolds, and the way you balance your system is you squint and look out across the entire thing and go, is that bubble column bigger than that bubble column? We make it easy to balance, and we also make it easy for the operators to make different decisions. So in the case on this reservoir, sometimes they actually slow down the airflow close to their intakes. If they're having a high amount of turbidity come in with their source water, they'll actually slow down or even shut off a few diffusers to increase settling for part of the year, and turn up the ones closer to the to their intake into their plant. So it just gives operators more flexibility. We really think it's important that the systems, like in my experience, operators are some of the most creative problem solvers that I've ever come across. Like they're good at dealing with issues. If you give them the tools, they'll figure out ways to make it work even better. So this is the results of the long term. You can see. This is when we replaced the aeration system. This is their long-term spikes in manganese. This is what we've done since then. We've taken just about all of the spikes out of their manganese in reservoir. Could we do more in reservoir? Possibly. They really need to replace their compressors and their infrastructure in the berm. But given what we had to work with in the budget that we had to do, we accomplished our goal. Now, there's things that we want to do to improve this more over time. We would love to see them get turbo blowers in to increase the energy efficiency of their system. With the existing infrastructure, we can't. There's too many leaks in it. There's too much back pressure. It wouldn't work. If we can increase the airflow, we might be able to help with the LJ more. You know, in addition to just managing nutrients, we could actually possibly create some turbulent mixing and get a switch over from cyanobacteria to green LJs. And this is just year over year, manganese levels, 2019 and 2020 being prior to the kind of the yellow and the red being prior to the system being installed. And then partway through the red year, we installed the system, and you can see since then, the green and the blue lines are showing a significant reduction in manganese, which was what we actually predicted in terms of before we put the system in. I'm gonna let Dhaval take over this one.
So this is a case study that I was talking about earlier, that sometimes you are putting a system, it's running for 20 years, 30 years, but it's still not reaching to the goal where it's still not reaching to the goal. So one of the example, this is one of the Silver Lake in United States, and the surface area was 95 acre volume, meter mean depth and maximum depth. We will focus on this part. Airflow 119 CFM. Deepest area of the lake, they were putting all the airs into the 12-meter deepest area of the water body. So basically they have the compressor over here, they were running the big hose over here, and this is the deepest area of the water body, and they were just assume that by we providing the more air on the deepest part, it will just solve the problem. Basically they were installed in 1982, bottom diffusion. And this is a case study, like I got it, this is a quote, like based on their language, that one of the main goal of the project was to reduction of blue-green algae and microcystin, which was not achieved with the 1982 aeration design. So basically they spent a bunch of, at that time, maybe $100,000 into the system. Now they are out of budget, they cannot improve or do anything. They were just hoping for best that maybe eventually it will solve the problem. The new system that was suggested by, like, if we look at the airflow, it's not a great 119 CFM, 168 CFM, but the number of diffuser is 41. To solve the issue on this, like they needed, like, this is the map of the diffuser, that 41 diffuser they needed basically just, and it was replaced in 2014. So if we look at the chlorophyll and microcystin graph, it's just, since then, it's just going downside. Basically, airflow was almost equal, like they would have worked with 112, but the main factor over was the diffuser, number of diffuser. Like instead of putting at one place, they did it in 41 smaller, and it's just showing them the result. If we look at the TSS, in 2014, in August, it was 32, and within 1 year, it's 1.4. Dissolved O2 was 12.71 at surface, and at the bottom, it's 0.06. Basically, there was an anoxia happening at the bottom. And right now, after 1 year, 7.69 on the surface and 3.17 at the bottom. So classic example of, like, they ran system for more than 30 years, never able to solve the problem of blue-green algae, but just changing the number of diffusers, they were able to get the result they wanted to.
Yeah. So this is a fairly recent project for us, probably 6 years in the making. We spent a lot of time working with this group, just a residents association in Langley, BC. This is an old gravel quarry that was allowed to fill up with water, and they turned it into a lake. It is a stormwater basin. They call it a lake. It is 100% a stormwater basin. Their inflows come completely from stormwater runoff through a combination of agricultural and municipal land. Had pristine water quality for, I think, was it 60 years it was in existence? So pristine water quality for about 60 years of existence. And about 7 years ago, they started to get regular blue-green algae blooms in it. And they came to us, amongst a few other people were involved in the consultation process, which is why it took so long. But we explained what had happened. They'd reached the point in time where the productivity had gotten to the point where they had so much organic accumulation in their sediments that their sediment oxygen demand, there was no way to prevent hypoxia and anoxia from occurring at the sediments. They're getting massive nutrient redox out of the sediments. They're getting high levels of ammonification. And we were able to, this year finally, so this gives you, these are your DO and temperature profiles from beforehand. So you can see they sample in 3 spots around the lake. And this is different times of year that they've done the sampling. That's why there's multiple columns in each of them, but you can, your temperature is your dotted line and your dissolved oxygen is your solid lines. And the interesting thing that we see is when we get to depth in here, even though, because they kept telling me, oh, our water body, it's fully homogenized. It only mixes once a year. It only stratifies in the summertime. And I'm like, you guys have so much sediment and oxygen demand year round that you are often going to be getting low dissolved oxygen levels when you get deep enough. And so even in times when they were having a homogenized water column, they were still seeing some sediment anoxia happening. This is the system we installed. I'm actually glad it took as long as it did, because if we'd put in the system that we had originally thought of for them back when we were first talking to them, it actually would have been undersized and it probably would have made their water conditions worse. So we learned a lot. Again, it was bringing Dhaval on board and doing the research. The thing I'll point out is you notice how these are all different sizes, these circles? It's because we have good bathymetry on this water body. We were able to design the system, and there's going to be some blank spots because it just got too expensive to fill in all of the holes. But the ultimate goal of this is to fully homogenize that water column, to overcome that density differential, have enough energy to turn it over. And because we knew the depths, we could say this is how much area around each diffuser we can count on there being positive far field effects. There was no way that we were going to, just given the sheer size of the water body, if we wanted to actually overcome the positive buoyancy of blue-green algae and mix it well enough to deal with the blue-green algae problem, it would have been a jacuzzi. Like it just would have been a rolling boil, which isn't realistic, both in terms of energy consumption and capital cost up front. It just wasn't realistic. So we don't have a lot of data after because it's new. It was just installed this spring. But we are in the middle of the summer now maintaining full homogenization in the water column. And I warned them about this beforehand. I said, you guys need to understand. So if we get right down to the sediment levels, we are still seeing the sediment oxygen demand being too much for the aeration system to overcome. So we are seeing at the very, very bottom of that sediment water interface for about 2 weeks a year, we are seeing the aeration system not being able to fully deliver oxygen. The choice that they had was, okay, we can put it in an oxygenation system. It'll cost you 4 times as much money. Can you live with 2 weeks per year where you're going to have, you're going to drive some poor water quality, at least for the first probably 3 to 7 years of operation? It's hard to predict that. There's a huge amount of organic sediments. Their plan originally is to run this thing just in the summertime. We've told them run it 24/7, 365 until you can get to the point where you have degraded the nutrients enough in your in the deepest parts of the water body year round, so that you eventually get to the point where in the summertime you can meet the oxygen demand. At that point in time, you can start running the system intermittently. You can set it so that in the winter months you turn it off altogether. In the spring and fall you only run it a few hours a day, and you only run it full time through the summer, so you get better energy efficiency. But to us, this is overall a success story, given the budget that they had to work with, the goals that they had, and them clearly understanding that there's still going to be issues, that the aeration system by itself, without them adding, either they could add some surface aerators, which might help in the summertime, or fountains. They could add some treatments, but on its own, the system's doing exactly what we expected it to do. And again, this is the before and after overlays, and it's just showing that before we were seeing some significant stratification in the water body temperature wise. We in the summer months or in the warmer months, we are now fully homogenizing. What did I do? Is that me or you guys? I lost my screen. Everything's off up here, so. All right, we're good. So we'll do without screens. It would be nice if we had the last points to touch. I think what we're trying to get across to you guys more than anything else is water's complicated. Every single water body is different. Make data-driven solutions. So one of the things that we honestly really suck at in Canada is having good monitoring data from our surface water bodies. We have the technology now where, yeah, it's expensive to go out and do water chemistry every single week on a water body. We now have sensors we can put in for a relatively low cost that will give you real-time monitoring data that allow you to make more informed decisions. There are cases, for example, small stormwater bodies. The monitoring doesn't make a lot of sense. The end solution is probably going to be anywhere from, let's say, a small stormwater body. Between treatment and aeration or oxygenation, you're probably under 50 grand upfront investment. If you're going to do a full study on that water body, it'll cost you more money in study than the solutions will. And that's where our experience or dealing with an experienced company comes in. I can walk in and I can look at a stormwater body that's, say, an acre in size or 3 acres or 5 acres inside. I can look at the level of productivity it's having. I can look what's growing in it. And based on my experience, I can make a pretty good guess as to what we need to do to solve it. And then Dhaval can take a lot of assumptions. In other words, we know the average sediment oxygen demand of most water bodies in the prairies is a certain amount given a certain amount of productivity. So we can still create models and still give you a fairly clear idea if it's going to work or not, because again, sometimes huge monitoring programs and scientific studies just cost money. If you're dealing with a bigger raw water body, whether it be a lake or a raw water reservoir, invest in the data, because if you don't invest in collecting the data, you at best have if you're talking aeration, 50-50 chance of it doing what you want it to do, because it'll be very, very hard to design and size it without good bathymetric mapping, good DO and temperature profiles, decent water chemistry, and at the ultimate end, good like sediment coring, phosphorus fractionation data. I think, is there anything else you want to cover on? Yeah. So I think we've covered on why systems fail. We've made lots of mistakes over the years. We've tried to learn from them. We tried to stand behind the mess ups we've had. Because of that, we've gotten very, very good at not having those anymore, because they're really expensive for little companies like us. But when it comes to you guys and your perspective, please just follow data. Let science lead you to the solution. There's an expression that if your only tool is a hammer, every problem quickly becomes a nail. We used to be like that. It used to be, we made aeration systems. That's what we do. And we believed that they were, they always worked, and water bodies were so similar to each other that we could do the same thing in every one and we get results. We know now that that's not the case. So when you guys as operators, you're dealing with stormwater, raw water, recreational ponds, whatever, understand your water body or find somebody. Generally, we recommend not using us to understand the water body, because that would create a conflict of interest. There are lots of great environmental firms out there where you can get them to collect the data, them to do a study. They can do nutrient budgets. They can do your oxygen work. You give us that data, we can come back to you and tell you what will work, what won't work, and hopefully, help you guys actually solve the problems you're dealing with. So, any questions at the end? Because I think we're out of luck when it comes to the projectors. So, is it? Yeah. We don't have time. Yeah, we don't have time to go at. So it's just, is there any questions you guys have? Anything you want to know? Any more detail on anything? Some people are hungry. All right. Well, thank you very much. Really appreciate you guys sitting in and. Oh, do we?
Hello. So we just have one online. It's a comment from CJ. Says, my parents live on the Sunrise Lake, and they are saying that the water quality is a lot better this summer than last summer. So it seems the water quality is definitely improving, and it will take a few years for the water quality to become great.
Yeah. So like I said, Sunrise, I appreciate the comment. We did see an actual worsening where they had one of the worst algae blooms they've ever had this summer. And we told them in advance that they were going to see it, but most of the summer they did see improved water quality. The aeration system did what it was supposed to do. It's just going to take time to overcome that sediment oxygen demand. So really do appreciate the comment.
Folks, so I'd like you to give our presenters a warm round of applause for this great presentation.
Thank you.
Thank you so much, Dhaval. That was
very much.
really great. Thank you.
Thank you.
And thank you. That was really informative.
Thank you.